everyone, welcome to our channel Knowledge of Friends. Subscribe to our channel and click the bell icon for the latest update. Today we're going to start with your class, that is your chemistry here, and that is your class 3. As you know that we had done your class 2 and where we had completed the unit 1 here, that is the name of the unit is your solid state, and where we had completed that and some of the few questions and some of the summary related to this unit 1 which we have to cover up. So we will be going ahead with unit 1 as well as we will doing unit 2, and we'll start doing unit 2 as well. So first we'll complete unit 1 and then we'll start discussing about unit 2. Before starting with this, it's a huge request from my side to all the viewers, please go through with the subscribe button and please like, share and subscribe to our channel so that many maximum people can get the information at once, and even though you can also enjoy the video as well. So here we go ahead with the first question of the unit 1 here, that we have that all total, that is your 19th question, and that we had solved, that is the another one, where what a type of defect can arise when a solid is heated, which physical property is affected by it, in what ways, that you have to find out. The other is what type of a stoichiometric defect is shown by ZNS and AGBR. The other question is explain how the vacancies are introduced to an ionic solid when a cation of higher valence is added, an impurity in it. The next is ionic solid which have atomic vacancies due to the metal axis defect and develop color. So explain with the help of a suitable example. The other we have a group 14 element is to be converted into an n-type semiconductor by doping it with a suitable impurity. To which group should this imply that impurity belongs? And what type of a substance would make a better permanent magnet, ferromagnetic and a ferrimagnetic? Justify your answer, that what we have to justify here as well. We are in the same case that we have to go ahead in this. Some of the things related to the unit 1, which is the solids have a definite mass, volume and shape, and this is due to the fixed positions of their constituent particles, short distances and a strong interaction between them. In amorphous solid, the arrangement of the constituent particles have only a short range order, and consequently they behave like supercooled sequid and do not have a sharp melting point and are isotropic in nature. In crystalline solid, there is a long range order in the arrangement of their constituent particles. They have a sharp melting point and anisotropic in nature, and their particles have a characteristic shapes. Properties of crystalline solids depends upon the natures of interactions between their constituent particles. On this basis, they can be divided into 4 categories, namely molecular, ionic, metallic and covalent solids as well. They differ widely in the properties that we have. The constituent particles in crystalline solids are arranged in a regular pattern which extends throughout the crystal. This arrangement is often depicted in form of a 3-dimensional array of points, which is called crystal lattice. Each lattice gives the locations of one particle in space. In all, 14 different types of lattice are possible, which are called Bravell's lattice as well. Each lattice can be generated by repeating its small characteristics portions, that is called unit cell. And a unit cell is characterized by its edge length and 3 angles between these edges as well. Unit cell that can be either primitive, which have particles only at their corner positions, or centered. Centered unit cells have additional particles at their body centered. Body is centered as well, which is known as, and at the center of each phase, that is face centered, and at the center of the 2 opposite phases, which is end center. There are 7 types of primitive unit cells. Taking the centered unit cell also into an account, there are the 14 types of unit cells in all, and which results to the 14 Bravell's lattice as well. In the same case, the close packing of the particles results in the 2 highly efficient lattice, hexagonal close packed HCP and a cubic close pack, which is CCP. The latter is called a face-centered cubic, which is FCC lattice. In both of these packages, 74% space is filled, and the remaining space is present in the form of the 2 types of voids, octahedral voids and a tetrahedral voids. Other type of packing are not close packing and have a less efficient packing of particles as well. While in body-centered cubic lattice, which is BCC, 68% space is filled, and in simple cubic lattice, that is only 52.4% space is filled. As I told you, and we had just find it out as well, This is the short summary of unit 1, that you can go ahead and you can, what you had missed it out and what you have left it out for making notes, you can just go ahead. In the same case, solids are not perfect in structure. There are different types of imperfections or defects in them: point defects and line defects. They are common types of defects. Point defects are the three types, which is stoichiometric defect, impurity defect, and non-stoichiometric defect. Vacancy defects and interstitial defects are of the two bases of the stoichiometric point defect. In ionic solid, the defects are present as Frankel's and Schottky defects. Impurity defects are caused as the presence of the impurity in the crystal. In ionic solid, when the ionic impurity has a different valence than the main compound, some vacancies are created. Non-stoichiometric defects are of metal excess type and a metal deficit type. Sometimes calculated amount of the impurities are introduced by doping its semiconductor that change their electrical property. Such material are widely used in electronic industry. And solid shows that many types of magnetic properties like paramagnetism, diamagnetism, ferromagnetism, and antiferromagnetism and ferrimagnetism. These properties are used in the audio, video, and the other recording devices. All these properties can be corrected with their electronic configurations or structure as well. Now we'll go ahead with some of the questions here, and then after that we'll start with unit 2 as well. That is, the first question for this, we have define the term amorphous, give a few examples of amorphous solid. Next is, what makes a glass different from a solid such as quartz? Under what conditions could quartz be converted into glass? The other question, classify each of the following solid as ionic, metallic, and molecular network, covalent or amorphous as well. That we have tetramorphous, deoxide, graphite, ammonium phosphate, brass, SiC, rubidium, I2, LiBr, plastic, Si, that you have to classify. Then other than that, question is, what is meant by the term coordination number? What is the coordination number of the atomic atoms, like in a cubic closed packed structure and in a body that centered cubic structure as well? That's what we have to answer it out. The next question is, how can you determine the atomic mass of the unknown metal if you know its density and dimensions of its unit cell? Explain. The other question is, stability of a crystal is reflected in the magnitude of its melting point. Comment. Collect that a melting point of a solid water, ethyl alcohol, diethyl ether, and that is your methane from this data book. That is, what can you say that about the intermolecular forces between these molecules as well? The other, that is, how will you distinguish between the following pairs of terms, which is hexagonal closed packing and a cubic closed packing, crystal lattice and unit cell, tetrahedral void and octahedral void? How many lattice points are there in one unit cell of each of the following lattice, which is face-centered cubic, face-centered tetragonal, and body-centered as well? The other question, explain the basic of similarities and differences between the metallic and ionic crystal. Another one, explain ionic solids and are hard and brittle. Ionic solids are hard and brittle. The other question, calculate the efficiency of packing in the case of the metal, that for a simple cubic, body-centered cubic, face-centered cubic, with an assumption that the atoms are touching each other. Now we'll be having another question here, which is silver crystalline in FCC lattice if edge length of the cell is 4.07 into 10 to the power minus 5, then minus 8 centimeter, and density is 10.5 gram centimeter cube, and that is it. We have to calculate the atomic mass of silver. Where the other question is, a cubic solid is made of two elements of P and Q. Atoms of Q at the corners of the cube and P at the body centered. What is the formula of the compound? What are the coordination number of P and Q? These were the questions that I had done in the last class. That the solution of these particular sort of like similar like this questions. So you can do ahead by your side, so that I will get that are you able to do it or not. The other question is, niobium crystallizes in the body-centered cubic structure if density is 8.5 gram centimeter cube. Calculate atomic radius of niobium using its atomic mass 93 unit. If the radius of the next question is, if the radius of the octahedral void is r and the radius of the atom is a closed packing is capital R, derive relation between r and r, that's small r and capital R as well. We'll go ahead with other question. Copper crystallizes into a FCC lattice with edge length 3.61 into 10 to the power minus 8 centimeter. Show that the calculated density is in the agreement with its measured value of 8.92 gram centimeter cube. The other question is, analysis show that the nickel oxide has a formula of Ni 0.98 and O 1.00. What fraction of nickel exists in Ni2 plus and Ni3 plus ions here? The other question, what is semiconductor? Describe the two main types of semiconductor and construct their conduction mechanism. The other question is non-stoichiometric cuprous oxide, which is Cu2O. It can be prepared in the laboratory, and in this same code, that in this oxide the copper to oxidation ratio is slightly less than 2:1. Can you account for the fact that this substance is a p-type semiconductor? Other is ferric oxide crystalline is a hexagonal closed packed array of oxide ions with 2 out of every 3 octahedral holes occupied by ferric ions, and derive the formula for the ferric oxide. The other question, we have to classify each of the following as being either a p-type and an n-type semiconductor, where Ge depends within, that is ion, and Si doped with B, that is we have to find out here. Now the other question we have here in terms of it, where gold, like atomic numbers, radius is 0.144 nm, crystallizes in the face-centered unit cell. What is the length of the side of the cell as well? The other question, in terms of a band theory, what is the difference between a conductor and insulator, and between a conductor and a semiconductor? Another question, explain the following terms with a suitable examples: Schottky effect, Frankel's effect, the terrestrial and F-centers. Another question, aluminum crystalline in the cubic closed packed structure, its metallic radius is 125 pm. What is the length of the side of the unit cell? And how many unit cells are there in 1.00 centimeter cube of aluminum? Another question, if NaCl is doped with 10 to the power minus 3 mole percent of SrCl2, what is the concentrations of vacancies? Concentration of cation vacancies. The another and the last question of this, explain the following with a suitable example, which is ferromagnetism, paramagnetism, ferrimagnetism, antiferrimagnetism, and 12 to 16 and 13 to 15 groups compounds that we have to talk about it, which we had done even in the last class as well. Now we'll go ahead with unit 2. The name of the unit 2 is solution. That solution we have to talk about it. Let's go ahead with that. In solution here, we will talk about some of the things as like in a normal life, we rarely come across a pure substance. Most of these are mixtures containing 2 or more pure substances. Their utility or importance in life depends on their composition. For example, the properties of a brass mixtures of copper and zinc are quite different from those of the German silver mixtures of copper, zinc and nickel, or a bronze mixture of copper and tin. Here in this, we can say that the that is part per million, which is ppm of fluoride ions in water prevents tooth decay, while 1.5 ppm causes the tooth to become mottled, and a high concentration of fluoride ions can poisonous. For example, sodium fluoride is used in the rat poison. That is, intravenous injections are always dissolved in water containing salt at particular ionic concentration that matches with the blood plasma concentrations and so on. In this unit, we will consider the mostly liquid solutions and their formations. This will be followed by studying the properties of solution like vapor pressure, colligative properties. We will begin with the types of solutions and then various alternatives in which the concentrations of a solute that can be expressed in liquid solution as well. With reference towards it, first we'll go ahead to discuss about it, which is a types of solution here. So types of solution, in terms of types of solution that we have to talk about it here. In types of solution, the solutions are either homogeneous mixtures of 2 or more than the 2 compounds, And by homogeneous mixture, we mean that its composition and properties are uniform throughout the mixture, and generally, component that is present in the largest quantity is known as solvent, and a solvent determines the physical state in which a solution exists. One or more solvent determine the physical state in which solution exists, and one or more components present in the solution other than solvent are called solute. In this unit, we shall consider only a binary solution here. In the terms of binary solution, that consisting of the two components here, each component that may be a solid, liquid, or in gaseous state, and that will go ahead with the discussion about it. And we'll just first go ahead with a table where the types of solution we will discuss here. So here we have types of solution. First we'll discuss, as it is mentioned here only. So we'll just go ahead. Solute, solvent, and common examples. Now we will be going ahead further. So let's go ahead with this. The first, the types of solution we have is your gaseous solution. In this, the solute we have, if we have a solute gas and the solvent also gas, so the mixture of oxygen and nitrogen gas, mixture of oxygen and nitrogen gas. Okay, the other we have, if it is in the gaseous solution only, that if it is the solute is liquid and the solvent is gas, then that is chloroform mixed with nitrogen gas. Okay, the other we have, it is solid, and if it is gas, then camphor in nitrogen gas. Now talking about the second one, which is liquid solution. In liquid solution, if solute is gas and solvent is liquid, then oxygen dissolved in water, if it is that is your liquid and this is also liquid, then ethanol dissolved in water. If it is solid and this is liquid, then glucose dissolved in water. The other we have, which is the solid that solution. So in this, the solvent will be liquid, solid here. If it is gas and this is solid, then solution of hydrogen in palladium, solution of hydrogen in palladium. If it is liquid and this is solid, then amalgam of mercury with sodium. If it is your solid and this is also solid, then copper dissolved in gold. Okay, so this is the types of solution that we have discussed about it, which is the gaseous solution, liquid solution, and a solid solution here. Now we'll discuss about it with another one, and that what we have to discuss as well in the same case, which is the expressing concentrations of solution. Expressing concentration of solution. In this, the compositions of a solution that can be described by expressing a concentration, the latter that can be expressed either qualitatively and quantitatively. For example, qualitatively, we can say that the solutions is dilute, relatively very small quantity of solute, and or its concentration of this description that can be add a lot of confusion, and thus the need for the quantitative descriptions of the solution. There are several ways by which we can describe the concentration of the solution quantitatively as well. In the same case, we can say that the mass percent of the component will find out, and that is mass percent here, which we have as follows. The first we have mass percent, mass percentage, which is W by W. In this, the mass percentage of the component of a solution is well defined as, that is, we have mass percent of a component equals to, which is mass of the component in the solution upon total mass of the solution into 100. Okay, that we have. For example, if a solution is described by 10% glucose in water by mass, it means that 10 gram of glucose is dissolved in 90 gram of water, that resulting in 100 gram solution. Concentration described in the mass percent is commonly used in industry, chemical applications. For example, commercial bleaching solution contains 3.62 mass percent of sodium hypochlorite that in water here. Now we'll go ahead with the second categorization, which we have is your volume percentage. The second we have volume percentage, V by V. Here, if the cell here in this, that the volume percentage is to be defined as, which is as follows: volume percent of a compound equals to volume of the compound upon total volume of the solution. Into 100. Now, for example, 10% of ethanol solution in water means that 10 ml of ethanol is dissolved in water, such that the total volume of the solution is 100 ml, and solution containing a liquid are commonly expressed in this unit only. For example, a 35% volume by volume solutions of ethyl glycol, and that is your antifreeze, is used in cars for cooling the engine. At this concentration in the antifreeze lowers the freezing point of water to 55.4 Kelvin, which is approximately 17.6 degrees Celsius. Now we'll talk about the third one, which is mass by volume percent. Mass by volume percentage, which is W by V. Here other unit, that is another unit which is commonly used in medicine and pharmacy, is mass by volume percent, and it is the mass of the solute dissolved in 100 ml of the solution as well. Now we will be going ahead with the fourth one, which is parts per million here. Now we'll talk about the fourth one, which we have is your parts per million. So here, when a solute is present in trace quantities, it is converted to express the concentration in parts per million, which is we had represented as form of ppm, and that is defined as parts per million, that is equals to number of parts of the component upon total number of parts of all component of a solution into 10 to the power 6 here. Now we will be going ahead, as in the case of the percentage, the concentration in the parts per million, that can also be expressed as mass to mass, volume to volume, and mass to volume. A liter of a seawater which weighs 1030 gram and contains about 6 into 10 to the power minus 3 gram of dissolved oxygen, which is O2, and such a small concentration is also expressed as 5.8 gram per 10 to the power 6 gram, which is 5.8 ppm of a seawater. And the concentration of pollutants in water or atmosphere is often expressed in terms of that is milliliter inwards or ppm as well. We'll talk about the other one, which is the fifth one, and that is your mole fraction. So we'll talk about the fifth one here, which is your mole fraction. In terms of mole fraction here, your commonly used symbol for the mole fraction is x, and subscript used on the right hand side is x denotes the components, that is defined as mole fraction of a compound, mole fraction of a component equals to number of moles of the component upon total number of moles of all the components. So for example, in a binary mixture, if the number of the moles of A and B are Na and Nb, that respectively the mole fractions of A that will be, and that is represented by Xa equals to Na upon Na plus Nb. For a solution containing a one number of component that we have, so x1A n1 upon n1 plus n2 plus n3 till n of I, this is I, and that is equals to sum of n1 ni 1 upon ni here. So it can be shown that is your here in the same case that the given solutions sum of all the nodes fractions is unity, and that is represented 1x1 plus x2 plus x3 till x of I, and that is equals to 1 here. Mole fraction unit is very useful in relating some physical properties of solution, say vapor pressure with a concentration of a solution, and are quite useful in describing the calculation involving a gas mixture as well. And in the same case, we will go ahead and further that what we have to discuss here. In the same cases, as I told you, we'll do it solution the questions here, so that you are you able to do it or not, that you will be get to know about it. And then after that we'll discuss the another molarities, that is molarity and a molality as well. So we'll do the question for with reference towards with respect towards them as well. So let's go ahead here. So the first question here, this is for the unit 2 here, that what we have to discuss. The question I will tell you here, then I will write it down. The question is, calculate the mole fraction of ethylene glycol, which is C2H6O2, in a solution containing 20% of C2H6O2 by mass, that we have to find out. Let's go ahead with the question here. Calculate the mole fraction of ethylene glycol, which is C2H6O2, in a solution containing 20% of C2H6O2 by mass. So for that we have to solve it out. Assume that we have 100 gram of solution. One can start with any amount of solution because the results obtained will be the same, and solution will contain 20 gram of ethylene glycol and 80 gram of water as well, that they had mentioned you here. So with a molar mass of C2H6, molar mass of C2H6O2 equals to 12 into 12, कार्बन का 12 होता है, that is multiplied by 2, प्लस हाइड्रोजन का 1 होता है, that is multiplied by 6, प्लस oxygen we have 16 and that is 2 multiplied by 2. We'll solve it out, we'll add and out. 12 to the 24 and 6 1 6 are 6 and 16 to the, that is we have 38 here, and that is 32, sorry, that we'll add and on and we'll get here as your 62 gram mole inverse. Okay, so with the same references, the moles of C2H6O2 will find out. Moles of C2H6O2 equals to, which is 20 gram, which we had given, and 62 gram mole inverse. So here this is gram cancel, and when we will solve it out, 20 upon 62 will get 0.322 and mole will come here, so that is an inverse, it will become mole. The other we will talk about moles of water. That is equals to 80 gram upon 18 gram mole inverse, which is equals to 4.444 mole. Now we'll talk about for the another one, that what we have to find out, which is X glycol equals to moles of C2H6O2 upon moles of C2H6O2 plus moles of water. So that we have discussed about it, Na upon Na plus Nb, and that we are representing moles of C2H6O2 upon moles of C2H6 plus moles of H2O total content. So that we have 0.322, which we have find it out, upon, which is mole, so that is 0.322 mole, plus again we have find out 4.444 mole. We'll just go ahead, we'll find it out, that is your 0.068. Now further similarly we'll find out for the other one, which is the water. That is for water equals to, that is 4.444 मोल अपॉन, पहले हमने ग्लाइकल के लिए निकाला, अब वाटर के लिए निकालेंगे, एंड दैट इज योर 0.322 मोल प्लस 4.444 मोल, which is equals to 0.932. So mole fraction of water, that can be also calculated as mole fraction of water equals to 1 minus 0.068, and which is equals to 0.932. okay, as you can see हमने 1 से 0.6068 को माइनस किया, will get 0.932 as well. So as you can see here, and this is how you have to solve it out, and as you can check that your answer is right or not, and that also you can do it. Let's go ahead with the other discussion that we have to talk about the molarity. That is the another sixth one, and that is molarity. In terms of molarity, the molarity is denoted by the capital M, and that is defined as the number of moles of solute dissolved in 1 liter of 1 liter, or we can say that 1 cubic centimeter of a solution here. So we can say that molarity is defined as the number of moles of solute dissolved in 1 liter of solution. So we'll go ahead with the formula first. Molarity equals to moles of solute upon volume of solution in liter, that we have to find out as well. Here for example 0.25 mole liter inverse, or 0.25 that molarity solution of NaOH means that 0.25 moles of NaOH has been dissolved in 1 liter of 1 cubic decimeter here. Now we'll go ahead with the question for this as well, for in terms of molarity. That is the second question of the session, and that's what we have to talk about it. So here they calculate the molarity of a solution containing 5 gram of NaOH in 450 ml of solution. The question we have: calculate the molarity of a solution containing 5 gram of NaOH in 450 ml of solution. So let's go ahead with the solution here. Solution for this: moles of NaOH equals to 5 gram upon 40 gram mole inverse equals to 0.125 mole here. Volume of the solution liter, if I'm talking about volume of the solution in liters equals to 450 milliliter upon 1000 milliliter inverse. And using this we can go ahead with the formula, which is molarity equals to 0.125 mole into 1000 milliliter liter inverse upon 450 milliliter, and that is equals to 0.278 molarity, which we have 0.278 mole liter inverse. So we can say that 0.278 mole decimeter inverse here. Okay, that is what a decimeter inverse cube here. Now we'll go ahead with the other question, that is the another one which we have to talk about it, and that is in the terms of molality here. That is the seventh one. In terms of molality here, that is the molality which is denoted by small m, and that is defined as the number of moles of the solute per kilogram of the solvent, and is expressed as, which is molality equals to moles of solute upon mass of solvent in kg. And that is, for example, 1 mole kg inverse, or a 1 milliliter, that is your solutions of KCl, means that 1 mole, which is 74.5 gram of KCl, is dissolved in 1 kilogram of water. Each method of expressing the concentration of the solution has its own merits and demerits. Mass percentage, ppm, mole fraction, and molality are independent of temperature, whereas molarity is a function of temperature, and this is because volume depends on temperature and the mass does not. We'll go ahead with the next question with reference towards molality here. The question we have: calculate molality of 2.5 gram of ethanoic acid, which is CH3COOH here, and that is in the terms of it in 75 gram of benzene here. We'll have to go ahead with this same case. We will be having the third question here. Calculate molality of 2.5 gram of ethanoic acid, which is CH3COOH in 75 gram of benzene, that we have to solve it out. This is an NCERT question here. Molar mass of C2H4O2 equals to 12 into 2 plus 1 into 4 into plus 16 into 2, which is equals to 60 gram mole inverse. Mole of C2H4O2 equals to 2.5 gram upon 60 gram mole inverse equals to 0.0417 mole. The other mass of benzene in kg equals to 75 gram and 1000 gram kg inverse, which is equals to 75 into 10 to the power minus 3 kg. Molality of C2H4O2 equals to moles of C2H4O2 upon kg of benzene equals to 0.0417 mole into 1000 gram kg up inverse upon 75 gram, that is equals to 0.556 mole kg inverse. So now this is the third question which we had done in terms of molality here. Here we have another questions that we have to discuss as well, which is to calculate the mass percentage of benzene, which is C6H6, and a carbon tetrachloride, which is CCl4, if 22 gram of benzene is dissolved in 122 gram of carbon tetrachloride. The other question we have: calculate the mole fractions of benzene in solution containing 30% of mass in carbon tetrachloride. The other question is to calculate the molarity of each of the following solution, where 30 gram of CONO3 whole twice and 6 TH2O in a 4.3 liter of solution. The other is 30 ml of 0.5 mH2SO4 diluted to 500 ml. The other question is calculate the mass of the urea, which is NH2CONH2, required in making 2.5 kg of 0.25 model aqueous solution. And that is another question, that is calculate molality, molarity and mole fraction of Ki if the density of 20% mass per mass aqueous Ki in 1.0202 gram milliliter inverse. That we have to do it. This is the 5 question as I gave you as homework, and the 3 questions we had done as solution. Now we'll talk about in terms of solubility. In terms of solubility, the solubility of a substance is its maximum amount that can be dissolved in a specified amount of solvent at a specified temperature It depends upon the nature of solute and solvent as well as temperature and pressure. Let us consider the effect of these factors in solutions of solid or a gas in a liquid as well. Now we'll talk about it, which is the solubility of a solid in a liquid. So that we have to go ahead. Let's go ahead with that as well. First we'll talk about it, which is solubility of a solid in a liquid. So in this, that every solid does not dissolve in a given liquid, while sodium chloride and a sugar dissolve readily in water. Naphthalene and that is anthracene are not. On the other hand, naphthalene and anthracene dissolve readily in benzene, but sodium chloride and sugar do not. It is observed that polar solutes dissolve in polar solvent, and non-polar solute is non-polar solvent as well. In general, a solute dissolves in solvent if the intermolecular interactions are similar in the two, and we may say that a like dissolves like. When a solid solute is added to a solvent, some solute dissolves and its temperature increases in solution. This process is known as dissolution. Some solute particles in solution collide that with the solid solute particles and get separated out of the solution, and this process is known as crystallization, where a stage is reached when the two processes occurs at the same rate. Under such conditions, number of solute particles going into solution would equals to the solute particles that separating out a state of dynamic equilibrium is reached, which is, we can say that here, solute plus solvent becomes solution, makes solution here. In the same cases here, at this stage, the concentration of solute in a solution will remain constant under the given condition, that is temperature and pressure. Similar process is followed when gases are dissolved in liquid solvent. Such a solution in which no more solute that can be dissolved at the same temperature and pressure is called saturated solution. An unsaturated solution is one in which more solute that can be dissolved at same temperature. The solution which is in the dynamic equilibrium with undissolved solute is the saturated solution and contains the maximum amount of solute dissolved in a given amount of solvent, and that is, thus the concentration of solute in such a solution is its solubility. Earlier, we have observed that solubility of one substance into another depends on the nature of the substance. In addition to these variables, two other parameters, that is the temperature and pressure, also control this phenomena. Now we'll talk about it, which is effect of temperature. In terms of effect of temperature here, the solubility of a solid in a liquid is significantly affected by the temperature changes. Consider the equilibrium represented by, that is, this being a dynamic equilibrium that must be following the de-Chartiers principles, and in general it is a nearly saturated solution, and that the dissolution process is an endothermic, where that is your change in heat is greater than 0. The solubility should increase with rise in temperature, and if the exothermic, then the solubility decreases, and these trends are also observed experimentally as well. The second effect we talk about it, which is your effect of pressure. In terms of effect of pressure here, the pressure does not have any significant effect on solubility of a solid in liquid. It is so because solids and liquids are highly incompressible and practically remain unaffected by changes in pressures as well. We'll talk about the second one, which we have is the solubility of a gas in a liquid. Solubility of a gas in a liquid here. Many gases dissolve in water. Oxygen dissolves only to a small extent in water. It is this dissolved oxygen which sustains all aquatic life. On the other hand, hydrogen chloride gas, which is HCl, is highly soluble in water, and solubility of a gases in liquid is greatly affected by pressure and temperature. The solubility of a gas increases with increase of pressure. For solution gives that that gases in a solvent that consider a system that is shown like a lower part is a solution and upper part of a gaseous system at a pressure P at and temperature T, that assume the system that to be a state of dynamic equilibrium. That is, under these conditions, the rate of the gases present the particles entering and leaving the solution phase is the same. Now increase the pressures over the solution phase of compressing the gas to the smaller volume, and this will increase the numbers of gaseous particles per unit volume over the solution, and also the rate at which the gaseous particles are striking and the surface of the solution to enter it. The solubility of the gas will increase until a new equilibrium has been reached, resulting in an increase in the pressures in the gas above the solution, and thus its solubility increases as well. With the same case, if I'm talking about it, that is, your Henry was the first to give the quantitative relation between pressures and solubility of a gas in a solvent, which is known as the Henry's law. The law states that the constant temperature, the solubility of a gas is in a liquid is directly proportional to the pressure of the gas, where the Dalton and the contemporary of the Henry here that has included independently that the solubility of a gas in a liquid solution is a function of partial pressure of a gas. If we use the mole fractions of the gas in the solution as measured of its solubility, then it is said to be that the mole fraction of a gas is the solution is proportional to the partial pressure of the gas over the solution as well. With the same case, the most commonly used one, the Henry's law, states that the partial pressure of the gas in a vapor phase is proportional to the mole fractions of the gas X of the solution. So that I will write it down for you so that you will get it out. Henry's law state that at constant temperature the solubility of a gas in a liquid is directly proportional to the pressure of the gas. Okay, this is by Henry law. And what Dalton said that is mole fraction of gas in the solution is proportional to the partial pressure of the gas over the solution. Then what the Henry law stated that as well, that is the partial pressure of the gas in vapor phase, which is P, is proportional to the mole fraction of the gas, that has been X. So the formula for this we have, and if that is expressed, you can say that P equals to K of Hx. Okay, so in this here the Kh is the Henry's law constant, and if we draw a graph between a partial pressure of a gas versus a mole fraction of the gas in a solution, then we should get the joint plots over the type of like this. It will be in the form of and this is your the partial pressure of HCl by torr, and this is a mole fraction of HCl of its solution in a cyclohexane. With the different gases have a different KH values at the same temperature. This suggests that KH is a function of nature of a gas, and it is obvious from this that the higher value of the KH at a given temperature, the lower is the solubility of a gas in a liquid. It can be seen that the KH value that both of N2 and O2 increases with increase of temperature, indicating the solubility of gases as well, and in the same case with that increase with the decrease of temperature as well, and it is due to the reason that the aquatic specifiers are more comfortable in a cold water rather than a warm bottle. So we'll just make here a sort of a table where we discussed about these the values of Henry's law constant for some selected gases in water here. So we go ahead, and that we have here, which is your the gas, and then we have a temperature that is in Kelvin, the KH, which is your K bar, then we have a gas temperature, and then of course we have here is your KH, and that is car. So let's go ahead to solve it out. So that will go ahead, and we'll just we had just made a table here, sort of a table here. So first we talk about helium. That is 293 degree, 144.97. For argon, 298, and that is 40.3. Then for H2, 293, 69.16. For carbon dioxide, 298, 1.67. The other we have for N2, 293, 76.48. The other is formaldehyde, 298 and 1.83 into 10 to the power 4. For the another we have, we'll go ahead for the another one that we have to talk about it. The another gas we have here is your O2. For that we have 293, and that is your 88 point. For N2 we had here, which is as I 76 here. So N2 for N2, this is your O2 here. Again we have N2 here as well. Sorry, this is for N2 again, and that is we have here is a 303, and that is it is your we have at temperature 303, it is 88.84. okay, and for another one here is your, which is your methane, and methane, it is at 298 temperature, it is 0.413. For O2, I'll talk about it. At 293 it is your 34.86, but at O2 at 303 it is your 46.82, and here it is your vinyl chloride. For that at 298 temperature it is 0.611. okay, so that what we have to go ahead, you can just write it down, and then according to the temperature you have to write it down, the that is your the KH, the value of the KH here. We'll go ahead with a question here. That is the another question that we have to talk about it, and which is we have as follows. That is the question is, if N2 gas is bubbled through the water at 293 K, and how many millimoles of N2 gas would dissolve in 1 liter of water, and assume that N2 exerts a partial pressure of 0.987 bar. We give the Henry's law constant for N2 at 293 Kelvin at 76.48 K bar. That we have to go ahead, and as we had discussed about the K bar, let's go ahead with the question first. If N2 gas is bubbled to water at 293 K, how many millimoles of N2 gas would dissolve in 1 liter of water? Assume that N2 exerts a partial pressure of 0.987 bar, given that Henry's law constant for N2 at 293 Kelvin is 76.48 K bar. The solution for this we have, that is, the solubility of a gas is related to the mole fraction in an aqueous solution, and the mole fraction of a gas is the solution and calculated by applying the Henry's law. And thus for that, nitrogen equals to be nitrogen upon KH 0.987 bar upon which they had given you here 76.480 bar, and that is equals to 1.29 into 10 to the power minus 5. As 1 liter of the water contains 555.5 moles of it, and therefore it N represents the numbers of moles of N2 in solution. For that, we'll go ahead. X nitrogen equals to N mole upon N mole plus 55.5 mole, which is equals to N upon 55.5, and that is equals to 1.29 equals into 10 to the power minus 5, and N is the denominator is neglected as it is lesser than 55.5, so thus N equals to 1.29 into 10 to the power minus 5 into 55.5 mole, so that is equals to 7.16 into 10 to the power minus 4 mole, and that being representing here 10.16 into 10 to the power minus 4 mole into 1000 N mole upon 1 mole, and which is equals to 0.716 m mole. In terms of it, Henry laws finds a several application in industry and explains some biological phenomena. Notable among these are like to increase the solubility of carbon dioxide in a soft drink and a soda drink, that the bottle is sealed under the high pressure. The scuba divers must cope with high concentrations of dissolved gases while breathing air that at a high pressure underwater. That increased pressures increases the solubility of the atmosphere gases in blood, and when the divers comes towards the surface, the pressure gradually decreases, and this release dissolves the gases and leads to the formations and bubbles of nitrogen in the blood, and these blocked capillaries are created medical conditions known as bends, which are painful and dangerous to life as well. To avoid bends as well as the toxic effects of high concentration of nitrogen in the blood, the tanks used to the scuba divers are filled with air diluted with helium, which is 11.7% of helium and 56.2% of nitrogen and 32.1% of oxygen. At high altitude, the partial pressure of oxygen is less than that at the ground level. So this leads to the low concentration of oxygen in the blood and tissues of people living at the high altitude or climbers low. That is, low blood oxygen causes the climbers to become weak and unable to think clearly, and symptoms of the conditions known as anoxia as well. So that is, The another one we'll take about it, which is effect of temperature in this. In that, that is the solubility of the gases in liquid decreases with the rise in temperature, and when dissolved, the gases modelize the present in liquid phase, and the process of dissolution that can be considered similar to condensation, and heat is evolved in the process, and we have learned this last section, that is the dissolution process involves dynamic equilibrium and thus must follow Lee-Chartier's principle, as dissolution is an exothermic process and the solubility should decrease with increase of temperature as well. We'll deal with two other questions I will give you as a homework here, which is H2S, a toxic gas with a rotten egg like smell, is used for the qualitative analysis if the solubility of H2S in water at STP is 0.195 N, that is calculate Henry's law constant. The other is Henry's law constant for the carbon dioxide in water is 1.67 into 10 to the power 8 Pascal at 290 K. Calculate the quantity of carbon dioxide in 500 ml of soda water when packed under 2.5 atm carbon dioxide pressure at 298 Kelvin as well. Now we will be going ahead here, we'll end up with this. And as I told you about the chemistry, which is we are dealing with the class 12 chemistry, and that is the competition wise. Other than that, we are dealing with the software engineering, where we had completed the unit 1 and we had started with that in the next coming class we'll start with the that is your software engineering unit 2, and which is SRS. And other than that, we are dealing with the quantitative aptitude, where we had in arithmetical ability we had completed the operations on numbers, as well as that is LCM and SCF of numbers, and as well as decimal fraction, and we had started with simplification as well. You can go through with that as well. With reference towards it, we are dealing with the database management system, we are dealing with the AR diagrams as well, and in terms of reasoning, where we had completed your verbal reasoning, which has been divided into two, which is the general mental ability and the logic reasoning. And non-verbal reasoning we had started with, where we are in the third topic here. Series we had completed here, and that is your which is more than 1000 questions. And other than that, we are dealing with we had completed the analogy. We will complete it in the next coming class, and then we'll start with as classification of the that is your third topic of non-verbal reasoning as well. Other than that, if I'm talking about in chemistry of class 12 that we are dealing with, as I told you, we had done class 9th chemistry as well. In class 12th chemistry, where we have to discuss here, that is the unit 1, which we had completed in the solid state, where we had completed the general characteristics of solid state, amorphous and crystalline solid, classification of crystalline solid, crystal lattice and unit cells, numbers of atoms in a unit cell, closed back structures, packing efficiency, calculation involving a unit cell, dimensions, imperfections in solid, electrical properties and magnetical properties as well. In unit 2 that we had started with, in unit 2 that we had started here, and that is we had started in this class only, which is your solution here. In this solution topic, if I'm talking about here, that what we have to cover up, and in the same cases in the reference towards this, that what we have to cover up, where types of solutions, expressing the concentration of solution, solubility, vapor pressure of liquid solution, ideal and non-ideal solution, colligative property, and determinations of molar masses as well, and as well as the abnormal molar masses as well. In the same case, in unit 3 we have to cover up the electrochemistry, which is electrochemical cells, galvanic cells, last inculcation, conductance of electrolytic solution, electrolyte cells, and electrolysis batteries as well. In that same cases, the other two topics we have to discuss in this, that is your fuel cells and corrosion as well. In your fourth unit, which we have to discuss here, that is your chemical kinetics. In the chemical kinetics, we have to deal with that is your rate of chemical reaction, factors influencing the rate of reaction, integrated rate equations, and pseudo first order reactions, temperature dependence on the rate of the reactions, and collision theories of the chemical reaction as well. Other than that, we'll deal with the unit 5th, which we have to discuss here, which is surface chemistry, where we have to cover up the adsorptions, catalysts, colloids, classifications of colloids, emulsions, and colloids around us. In unit 6, which is general principles and process of isolations of elements, which is we have to discuss the occurrence of metals, concentrations of ores, extractions of crude oil from the concentrated ore, thermodynamics principle of metallurgy, electrochemical principles of metallurgy, oxidation, reduction, refining, uses of aluminium, copper, zinc, and iron. Then that is unit 7, which we have to cover up the P block element. We have group 15 element, dinitrogen, ammonia, oxides of nitrogen, nitric acid, phosphorus, allotropic forms, phosphoric, that is phosphine, phosphorus halides, oxalates, oxoacids and phosphorus. Group 16 element dioxygen simple oxides. Ozone, sulfur, allotropic forms, sulfur dioxide, oxoacids of solids. Sulfur, sulfuric acids. Group 17 elements. Chlorine, hydrogen chloride, oxoacid of halogens and interhalogens compound, and group 18 elements as well. With a reference towards it, we have to cover up the unit 8, which is the D block and F block element, which is in that positions in the periodic table, electronic configuration of the D block element, general properties of the transition element, some important compounds of transition element, the lanthanides and actinides, some applications of D and F block that elements as well. Other than that, what we have to cover up here is another one, which is your unit 9, that is a coordination compound, where we have to cover up that is Warner's theories of the coordination compound, definitions of some important terms pertaining coordination compound, nomenclatures of coordination compound, isomerisms of coordination compound, bonding in coordination compound, bonding in metal carbohydrates, stability of the coordination compound, importance and applications of coordination compound as well. And then after that we'll continue with the unit 10, unit 11 and so on till that what we have in the syllabus as well. So first of all, it's a huge request from my side to all the viewers. Please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even you can also enjoy the video as well. As you know that we are dealing with many of the different subjects simultaneously, you can go through with that playlist. And it's a huge request from my side to please go through with the subscribe button and please like, share and subscribe our channel. So thank you, hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion in the comment box. Thank you.